Okay, we're starting. We're going to jump into chapter 2, which is the long-awaited moment. This is actually the chapter where we're actually going to learn some calculus. Finally. The first section, though, is not about calculus. It's about something else. But it's a good segue into calculus, and it's something you've seen before. We're just going to apply it in a slightly different way. So we're doing 2.1. It's titled Measuring Change and Rates of Change. There's one application we'll need from this, so we're not actually going to spend a lot of time here. Just want to talk about something called average rate of change. Does anyone happen to know how to compute the average rate of change? Exactly. It's a difference quotient. So let's discuss this a little bit, what that actually means or what it would involve. Right, you can think about it. So let's say your function is doing something weird. Right, it's doing whatever it wants to do. And you want to care about how this function is behaving on some interval a b. Right, so the interval is going to be given to you, and you want to examine the function. But you don't just want to examine it specifically at each point and know exactly what's changing. You want to know how does it change on average. Right? So the a's will have the output f of a, the b will have the output f of b. So we can measure the actual change of the function by just finding the difference here, and we'll see how the function itself is changing. But if you want the average change, you want to divide that out by the inputs. So essentially what you're going to have to do get is the overall slope, right? You're going to take the rise divided by the run. And this tells you how you're changing on average. How is the y value changing per 1 unit increase of the x value? It's basically what this is happening. So your function doesn't have to follow this line, but it can do whatever, but on average it goes from this point to that point. So on average we could talk about the behavior of this function. And in some cases that is beneficial to look at things that way. In other cases you need to be a little bit more specific, but it's an important idea to talk about. So it's kind of in situations where you want to kind of take the long view and look at the long term, how things are going, instead of worrying about the everyday minute details. You can look at the average rate of change, you can figure out how a function is behaving over some large amount. Yeah.
How do you pick the points A and B?
Well, it'll be given.
Okay.
So if I'm giving you a problem like this, I'll tell you what the points A and B are. But in general, if you're studying something and you want to know what's going on in average, usually you'll have a time frame in mind, so you'll pick the interval yourself to deal with whatever you need to do. But in this class, if I ask you to compute the average rate of change, I will give you the interval. So it has to be given, right? So you can't just find the average rate of change in general, it's the average rate of change on a given interval, right? So that'll have to be given to you at this point. There's another formula where that's equivalent to this one. So this is the other version of the difference quotient. f of x plus h minus f of x over h. It's exactly the same kind of formula, exactly the same kind of rule. The difference is how you're looking at it. In this case, you're measuring this function. You now look at it as in terms of the distance between the x values. So h is the distance between the x values. So I'm going to pick a first value called x, move a distance h to get to the second value, which is now going to be x plus h. So this will be f of x plus h. That will be f of x. And then when you find the average rate of change, which ends up being the slope, the rise over the run, you end up with y2 minus y1 over x2 minus x1, you end up with this formula. In this context, if you're given average rate of change, this is by far the most common formula to use in this one, because these are the numbers you'll be given, and you'll just plug them directly into this formula, so it's nice to do it this way. There are other contexts in which we'll prefer to do it this way, but it's largely by convention and tradition. They're both kind of the same, just a matter of perspective, really. But they both kind of measure the same thing. How does a function change on average over some interval? Let's do an example here. Very typical example, and if this shows up on a test or a quiz, it's not going to be any more complicated than this. So you can say something like let f of x equals x squared plus 1. Find the average rate of change on one. So that's an example. Right? It's never going to be any more complicated than that, really. The only difference is a function will have to be given to you. They would have to mention average rate of change, or I'll mention average rate of change. The only kind of variation in a problem like this is how you're given the interval, which it's just a matter of knowing how to read it. So you might be given the interval just like this, as an interval. You might be given something like, for x between 1 and 4, right? That might have been how it was phrased. Or you can say, from x equals 1 to x equals 4, or something like the point where x equals 1 to the point where x equals 4, etc. Right? But it's exactly the same information, it just might be phrased in a different way, but that shouldn't confuse you. At the end of the day, what you should recognize is that the A will be the left endpoint and the B will be the right endpoint. Right? So the smaller value you're going to take to be your A, the larger value you take to be your B. Right? But it will be given to you in one way or another. Okay? So you'll be given a function, you'll be asked to find its average rate of change, you'll be given the interval in some version of this. The right endpoint of the interval, that's your B, the left endpoint is your A, and you're literally just plugging into the formula that I erased right here. And it's not going to be any more complicated than that. Average rate of change isn't really going to, it might be something like in one part of a question, I might just throw it out there just to give you points, but it's not the focus of this class, because calculus is concerned with something that's called the instantaneous rate of change. So not how you're changing it on average, but how you're changing at an instant. But we kind of use this idea to help us figure that out. So it's something that should at least be mentioned. Okay. So here, how do I find the average rate of change? Just use the formula for 1. F of B minus F of A over B minus A. Now I expect you to have this memorized by now, but just in case, when you want to get to memorize something, you write it down all the time. So every time we're going to use a formula, we just copy down the general form. Okay, and then what? What is it? B now. Yeah?
F of B is 4 squared plus 1, which is 17.
Well, let's just write it down. F of 4 minus F of 1 over 4 minus 1. And so now you're telling me what? f of 4 is?
17.
So it's 4 squared plus 1, which will give you 17, minus
4 squared plus 1 is 2.
over 3. Is that okay? It's not okay. What's missing? Parentheses. Okay. So now it's okay. 1 minus 1, so you have 16 minus 1, that's 15. So this gives us 15 over 3, which gives us 5. And what does that number 5 mean? It means on average for each increase in 1 unit of the x-axis, the y-axis will jump by, the y variable will jump by 5 points. Right? And that's significant here that this is a positive. Right? So this means that this means on average y increases by 5 units every time x increases by 1 unit. And you can always sort of think of the average rate of change in those terms. The difference is this number here will change depending on the function and the interval you're looking at. So on this interval, if we're between 1 and 4, for every 1 inch the x-axis moves over, the y will jump up by 5 inches, right, or whatever units you're working with. So you can actually see that here. So actually know what this function looks like. This is x squared plus 1 around the interval 1 and 4. Notice that here, this output is 2. Here, this output is 17. Notice that the gap between this is 15. So the run here is 3. So roughly, there are 3 jumps of 1 units between these two. Usually, so roughly speaking, between each jump here of 1 unit, you'll make 5 jumps here. So your graph should be, roughly speaking, around the 7 mark here, roughly speaking, around the 12 mark here. But again, the graph could essentially be doing anything here. You're talking about on average. On average, if you were to draw the slope that connects the two, this would connect to that line around 7. Any questions on that? And that's it for 2.1. That's literally all we needed from that section. Just have to mention this application of the difference quotient. So if there are no questions, we will move on. And now we start calculus. For the next few classes, though, it's not going to feel like it because there's going to be an underlying concept that's being applied in calculus that we need to kind of understand. So we're going to work on understanding that first, and then we'll actually jump into things that are conventionally spoken, or are conventionally thought about when we're doing calculus. So if you were to ask someone, what is calculus about? What is it the study of? Basically, to say that in a phrase, what calculus is, what we will ultimately be doing in this course, is where we'll be studying things called derivatives and integrals and their applications. And it turns out that those are the 2 main components in calculus, and I'll talk a little bit more about what they mean and how they actually fit into the entire thing and what they're meant to accomplish. But it's important to note that if you were to force a 1-word answer out of somebody as to what is calculus the study of, the answer would be limits. Because the derivative and the integral, as you'll see later on, are in fact defined as limits. So we need to understand limits in order to understand what a derivative is, what an integral is, how they work, and why they work the way they work. Now, the idea of a limit is kind of a fuzzy idea. In higher mathematics, they'll make it a lot more specific, but for us, it's going to be kind of a very fuzzy, intuitive idea that we just have to get used to working with. So we're going to go through 2.2. We'll play around with the concepts a little bit, get familiar with the ideas that we're working with and strategies of how we want to look at things. and then we'll start to make things more like a math class. Here's a definition. This is the formula. And you'll kind of have an idea in the background of why it has to be the way it is. So let's actually start there. Not the official definition, but here's a fuzzy definition of what a limit is. The limit as x approaches a is just a number, of f of x is, and here's what it is, the y value that f of x approaches as x gets close. That's what a limit is. Okay. Now there are a couple very key words here that you have to pay attention to. One is the actual phrase, the limit as x approaches a of f of x. That is literally a phrase that we will be using. And when I talk about it, that's how I'm going to say things. Oh, the limit as x approaches 2 of this function, or whatever. Right? So that's kind of going to be the actual phraseology that's used. Some other words to keep in mind in this definition is the word the. That's going to be very important to us. Right? The limit has to give us an answer, kind of like a function where there's only one answer. The limit should only really give us one answer. We should kind of know where we're heading when our x value is doing something. So the idea is, I have a function and I'm manipulating the x value, I'm pushing it close to some number, and I kind of want to see how the y value is behaving at the same time. That's what the limit is. One other thing that's super important in this definition is the word approaches. Getting close. Right, that's a very, very important idea about limits. In fact, that's what makes limits kind of an idea that's kind of unique from what you've been studying in math, because usually math is all about, okay, if x is 1, what is y? You plug in 1, you get y. You never really had this idea of, what if x is close to 1? You're not quite there yet, but what if you're super close to it? What is the y getting close to? Right, so it's kind of this weird kind of fuzzy notion, then it's like, what do you mean close? How close is close? And it kind of gets vague. There is a way to make that more precise, but it won't matter to us. But this is a very central to the idea of a limit. It's you tracking the y value when the x value is doing something, and it's not important to actually get there. It's just important to approach there, right? And that's kind of an idea that we need to get through, really understanding. So let's actually just play around with a few examples and kind of understand this idea, because it's a very important idea. And the fact that we can actually get close to something is something that's very peculiar, actually. But it works in calculus with the kinds of functions we're using. So we're going to do that. So let me tell you about the notation first. This is how we denote this idea. The limit as x approaches a of f of x. We will write down lim. Below it we will write x, a little arrow, the number a, and then we'll write the function right beside it. So this is read as the limit as x approaches a gets close to a of f of x. What you can think of this as is the y value we approach. As x gets close to a. So that's sort of how you want to think of a limit. It's a very fuzzy notion at this point, but we will be doing strategies where we can actually figure this answer out. You might put parentheses here if your f has multiple terms in it, separated by pluses or minuses. But if you only have like one compact term, it's okay to just write it right beside the limit. Okay, so let's actually learn how to deal with these things by just jumping into some examples and seeing what we can come up with. So here's an example. The limit as x approaches 1 of the function x plus 1. So in other words, when I write that down, what you should be thinking of is when x gets close to 1, what is the function x plus 1 getting close to? The y values of this one. What do you guys think the answer is? What do you think the answer is? 2? Okay, that seems to make a lot of sense to me. Let's actually look at it from the pictorial perspective. What does x plus 1 look like? It's a straight line. Y-intercept is 1. Slope is positive 1, so it's going up as you move from left to right. Passes through 1 here. And here's where my x value is equal to 1. Now it seems to make sense that if my x is close to 1, the answer should be 2. Because I can actually literally plug that 1 into the function, and the output would be 2. Okay? But here's how I want you to think about it. I don't want you to always think about it as plugging in. I do want you to think about it as we inch closer and closer to 1, what is the y value inching closer and closer to? Right? And if I'm inching closer and closer to 1 here, what is that y value inching closer and closer to? Right? That's how you're going to want to think about it. So it's not just a matter of plugging in. And I'll give you, in my next example, you'll see why this is going to be an issue. But it's really about getting close. And so you can say, as x gets close to 1, our y will approach 2. Therefore, I can say that this equals 2. I can say that the limit equals 2. This is how I want you to think about it, not just as plugging in the number. So you sort of look at what your x values are doing, and then you look at what your y values are doing. And you can also think of something like a table of values, if you want, right? And what if I'm getting close to 1? You know, 0.9, 0.99, 0.999, right? And then what is the y doing, right? You realize that the y would be 1.9. 1.99, 1.999, right? Now here's a slot where there's the 1, and I really don't care what's going on here. I don't care. In terms of a limit, I don't care what's going on at 1. But from either side, I do care. So if I have 1.1, 1.01, 1.001, 1.0001, notice that the y value would start at 2.1, 2.01. 2.001, 2.0001. You'll notice that these numbers are all zooming in on one number, right? And it turns out that the closer you get to 1 from either side, the closer this value will get. It will approach 2, right? That's how I want you to think of a limit, not just like directly plugging something in. Okay? It's about getting close to something, approaching it, and really being careful of inching towards a destination, probably never getting there, but inching towards it and see how the function is behaving as you're doing this. That's the idea of a limit. Let's do another example. Look at the limit, again, as x approaches 1, of x squared minus 1 over x minus 1. Now what do you think the answer is? Now here you'll notice that I actually cannot plug in x equals 1, right? Because I would divide by 0, it's not defined. But the thing is, I don't really care about being at 1. That's not what a limit is concerned with, right? So the function at 1 doesn't make any sense. Yeah? Yeah, did you see something?
Function will be, so if we could cancel it out, it will create a pentacle, which allow us to limit as approach to 1, the value will be 2. Approaching, understand, approaching, not exactly.
Okay, so you saw that you can cancel here, right? Now, if we're at 1, we can't cancel, we're dividing by 0. It makes, literally, math doesn't work. But we don't care about being at 1, we care about being close to 1, so we can say, if x is not 1, then we can do the following. If I take the limit as x approaches 1 of this function, I could simplify. X squared minus 1 is actually something I could factor. It's the difference of squares. And I can kind of see here that that x minus 1 factor is now in both the top and the bottom. And as long as my x is not equal to 1, this is just a normal fraction like any other fraction. I can reduce this fraction. Right? And so that would be equal to the limit as x approaches 1 of x plus 1. We already knew what that was. That is actually the number 2. Right? We did that over here. Now, the difference between this situation and that situation is this point is not defined here. In fact, if you were to graph this guy, it would look like this. At 1, there is a hole. So I cannot actually get to the point where x is 1. Because if I get to the point where x is 1, I divide by 0. It doesn't make any sense. On the graph, how that shows up is a hole. And that's a technical term, by the way. They literally call it a hole. That's a rigorous mathematical term. Okay? So notice here, I can't actually plug in 1 because it doesn't make any sense, but I don't care about plugging in 1. A limit just cares about getting close to 1. So I'm getting close to 1 here. What is the y value getting close to? Right? If I'm getting close to 1 from here, what is the y value getting close to? And again, I could do a table of values. And in this case, the 1, I really can't get an answer. It's impossible to actually get an answer here. But looking at what the numbers are inching towards, I can actually figure out that the answer is actually 2. So this is a situation where the function itself doesn't make sense at the point of consideration, but the limit makes sense, right? Because even though we can't actually plug that number in, we don't care about plugging the number in. We just care about getting close to it. Let's look at another idea. Let f of x. This is a guy we've seen before. So piecewise function. It's one of the first examples I gave you of a piecewise function. Find limit as x approaches 1 of this function. What do you think the answer is? Yeah.
Does it not exist?
Well, what makes you say that?
Because when you approach it from different sides, the values are different.
Well, how do you know that? How do we actually, let's actually try to see what Lewis is seeing here. Let's actually draw this graph and see if we can actually picture it. Notice we have 2 intervals here of consideration. There's the interval 0 to 1. And then there's the interval bigger than 1, so everything to that side. How do we graph this? Quickly remind me how to graph something like this. Yeah?
0 to 1 is a horizontal line at 1.
Okay, so it means when you're on 0 to 1, you're graphing y equals 1, and that's a horizontal line. But you only care about, when you plug in the endpoints, you get this. When you plug in that endpoint, you get this, and you don't care about anything here. Right? You only care about the part between 0 and 1. Then you look at the other guy, y equals x plus 1. That guy looks like this. However, you plug in 1, that guy gives you at 2. Clearly here I can't really plug in 1, it's greater than. But I don't care about the left side, I only care about bigger. And so on the picture of the entire graph, it looks something like this. 1. At 1, this guy would start at 2. And then go off like that. So you said the limit doesn't exist. What was your reasoning?
Because as you approach it from the left,
Okay. So we're getting close to 1 from the left side.
yeah, you approach a y value of 1.
The y value is getting close to 1. So, right, so if x gets close to 1 from the left side, then our y value will get close to 1. Okay? And you do it from the other side. And what's going on now?
You're approaching 2.
Now, if you're on the right side of this point, notice that the y value is approaching 2. And this is where the word the comes into play in that definition. I said the limit is the y value you approach when your x value approaches something. Notice here our y value is approaching 2 different things. There is no the y value. We're approaching 2 different y values. There are several y values. And so this does not fit in with our definition. It's not possible based on our definition to actually write a number down. Right? So there is no the y value. This means, technically speaking, the limit as x approaches 1 of this function, you would say does not exist. That's often abbreviated DNE, right? And it does not exist. We cannot have an answer here because it doesn't fit our definition of what a limit is. A limit is supposed to give us a unique y value to be able to say, oh, the function is doing this when x does this. But we actually cannot say that here. So in this case, the limit does not exist. However, it's very important for us to know about the behavior of functions. So that seems kind of unsatisfying. Because clearly we can get an answer from approaching different sides, right? We can actually talk about what if we're below this value, what is the y value approaching? What if we're above this value, what is the y value approaching? We can actually have that conversation, right? To talk more about the behavior of the function. This leads to the notion of one-sidedness. And let me introduce you to the notation for that, and sort of we'll talk about what that means. Although you've seen an example here. So we can write lim x approaches a, and what you do is you write a superscript of a little minus sign of f of x. And what that is defined as, this is the limit as x approaches a from the left. Right? That would be talking about this guy. Figure out the point you care about, look to the left side and zoom in this way and see what your y value is doing. If there's an answer for that, you would write that here. Limit as x approaches a with a little minus sign. It doesn't mean you make the a negative. It's talking about a from the left. It's putting a power in a subscript. It's a notational thing. It doesn't really make any mathematical sense to do that, but it's a notational thing. So the other one is a with a little plus as a superscript of f of x. This is the limit as x approaches a from the right. So, in the above, the limit as x approaches 1 of f of x does not exist, but the limit as x approaches 1 from the left of f of x is actually the number 1. If I'm inching closer and closer to 1 from the left side, my y value is going closer and closer to 1. And if I'm approaching 1 from the right side, I'm getting closer and closer to 2. And limit as x approaches 1 from the right of x is 2. Right? But overall, the limit does not exist. This also leads to the notion of the existence of limits. limit as x approaches a of f of x only exists. You can only find an answer if the limit as x approaches a from the left of f of x exists, and the limit as x approaches f of a from the right of f of x exists, and they must be equal. So for an overall limit to work, this is an important idea that you have to understand, is that when you're approaching from the left or the right, you should be able to come up with an answer, and those answers should be the same thing. Otherwise, you end up with a situation similar to this, where your y values aren't agreeing, and you can't say, oh, it's approaching this unique y value. At this point, I also want to note it is possible for any or all of the following. To not exist, right? There are examples where this can give an answer but the other two don't, or this can give an answer but the other two don't, or this can give an answer but the other, well, this will never give an answer and the other two don't. But you can a lot of times mix and match it. We'll talk about some examples of that next time. You can think about some ideas. You can think about things like limit as x approaches -1 of radical x, for example. Or limit as x approaches 0 of 1 over x. And you can think about one side versus the other side and see what you can kind of get. Or limit as x approaches 0 of radical x. Right? So think about those ideas and how these three limits kind of play into that. And we'll pick up with that on Friday. We'll spend a while in limits, but right after that we'll jump into derivatives. We'll use this to actually define them. Yeah.
This
What?